For this example, we want to use a triple integral to find the volume of the solid inside the cone z equals the square root of x squared plus y squared over 3, but between the planes, that's a typo, planes z equals 1 and z equals 2. So let me show you the graph of this because it's kind of interesting. That's the example in between with the ice cream cone. There it is. Okay, so we have a cone right here, which is kind of that bigger gray cone kind of thing. And we have the plane at z equals 1 and z equals 2. And the way I did this was I plotted 3D of z right here, because if you're plotting in the cylindrical coordinate system and you plot just r equals z in the cylindrical coordinate system, you'll have a cone, right? So I've got my cone right there, and then I've got my plane z equals 1, z equals 2, because those are the regular rectangular coordinate systems that we know and love. But of course, I'm only graphing them for those circles. So that's how I get the circles in there. So it took some fancy mapling, that's a word, to do, but I did it. Okay, so I want to recreate this graph right here, and then I want to be able to find that integral. So the first thing I did was I drew the graph. I mean, it's not a particularly hard graph because you're really just graphing a cone and you've got two planes, z equals 1 and z equals 2. But remember that that would mean that, sorry, there's something cut off there, but it's rho cosine theta equals 2. There it is. Rho cosine theta equals 2, or excuse me, rho cosine phi equals 2, which means that rho is equal to 2 secant of phi, right? That's one of the definitions that we learn for a horizontal plane back at the beginning of the section. Horizontal planes, z equals 2 is the same thing as rho cosine phi equals 2. And similarly, z equals 1 would be rho cosine phi equals 1, which means that rho is equal to the secant of phi, because it's 1 divided by the cosine of phi, which is the secant of phi. Okay, so rho is kind of obvious. I mean, rho is going to go from blue to black. So it's going to go from a secant of phi to 2 secant of phi, no problem. And similarly, theta is kind of obvious. Again, we're doing the full revolutions around. We're doing basically the whole, all the top octants. So that means we're going to go 0 to 2 pi. We're not just doing like the first octant or something like that. So that's kind of obvious, no problem. The hard part is going to be phi. So the thing is that phi starts off at the top and it kind of moves its way out through the cone, and then it's going to stop out here, right, wherever that may be. So we need to figure out what that is. So let's start by reminding ourselves that when we have a cone, and we learned this at the beginning of this section, in cylindrical coordinates, when you have a cone is phi is equal to some constant k. Because phi is the angle from the top positive z-axis out. So if you set that in stone at k, then you just swing it around for theta equals 0 to 2 pi, the pink angle. So you're going to start phi equals 0 out to phi equals k, and you get that cone. All right, so we know it's going to be a constant, right? It's going to go from 0 up here at the top of the z-axis out to wherever that line is. We just need to figure out what that line is, right? Where is that at? So I'm going to draw the plane, and you can kind of see it right there. There's like a triangle that the cone forms with the YZ plane. So I'm going to draw that triangle in the YZ plane. So in the YZ plane, that cone would form this kind of triangle, right? So you're out y, whatever y is, you're up z, whatever z is, and phi is that angle between the positive z-axis and where the edge of the cone is. Okay, wonderful. Yes, but I know that z would be equal to the square root of, okay, now y is at 0 squared plus y squared. Well, remember, the cone itself has this as its rectangular coordinates. So if you're in the yz plane, then the x value will be 0. So it's 0 squared plus y squared over 3. So in this yz plane, x is 0. So you say z equals the square root of 0 squared plus y squared over 3, which is the square root of y squared over 3, which is y over the square root of 3. And that means that y is equal to, you multiply both sides by the square root of 3, y is equal to the square root of 3 times z. And that gives us that the tangent of phi, which is y over z, we learned that also at the beginning in the definitions for cylindrical coordinates. So y over z is the square root of 3, right? Because if you divide both sides by z, you'll get the square root of 3. And that means that angle's pi over 3, because we know that from the unit circle, that if the tangent is the square root of 3, then that angle is pi over 3, because pi over 3 has a sine of the square root of 3 over 2 and a cosine of a half. So the 2's will cancel and leave you square root of 3 over 1. All right, so all of that, a lot of trigonometry to get us to the point where phi is going to go from 0 to pi over 3. So here's our work here. We know it's volume. So the volume means that it has to be 1 as our equation. So it's going to be 1. The rho squared sine of phi piece is added in because we're using cylindrical coordinate systems. Not cylindrical, sorry, spherical coordinate system. So spherical coordinates means we have to throw in the rho squared sine phi. Then I'm going to do it with respect to rho first. Rho goes from secant of phi to 2 secant of phi. That'll get me from one horizontal plane to the other. Then phi is the hardest part to figure out, almost always, and it's going from 0 to pi over 3, from the top of the positive y-axis, which is 0, out to this angle that forms this side of this cone, which is pi over 3. And then theta is usually the easiest part. So theta is going from 0 to 2 pi because we're going the full cone, the full revolution around the positive z-axis. All right, now when I look at this whole thing, I see phi, right, rho and phi as in my limits of integration as well as my integrand. But I don't see any thetas anywhere. So my first step is going to be to pull 2 theta out of this thing. And then if I'm going to integrate this, I'm totally going to integrate it with respect to, well, actually, in this case, it kind of doesn't matter. I mean, phi and rho are kind of equally difficult. So pick one. It doesn't really make a difference. So I'm going to do it with respect to rho first. Why not? So if I did with respect to rho, that'd be 1/3 rho cubed. Then the sine of phi doesn't change, right? Because I haven't done anything with it. So I'm taking that from secant of phi to 2 secant of phi. So that means that I'm taking the integral of 8 secant cubed of phi, right? Because I'm substituting 2 secant of phi in there for rho. So 2 cubed is 8, and then secant cubed. And I just pulled the 1/3 out. You know, it doesn't help me any at all. So I put 2 pi over 3 out in front. And then I've got sine of phi minus secant cubed phi sine of phi. And I am totally making Maple do that. I am not doing that by hand. So to check myself, I made sure that I did it twice. You don't have to do it twice. I mean, you can, but I did the original integral after I'd put in the spherical coordinates, and I did it numerically as well. And then I'm doing the integral that I just ran into with 2 pi over 3, 8 secant cubed times the sine minus secant cubed times the sine, etc. And I did that one. And I'm getting phi, by the way, out of the, I think, out of the Greek palette. If not, yeah, I'm getting it out of the Greek palette, in case you're interested. It's right here, down there. And sure enough, I get 21.99 or 7 pi, and that will be my answer. So my answer is 7 pi. All right, all done.